Today we're going to talk about geometric sequences and series, and this is a topic that would have been covered in the high school curriculum, but it's really super important, especially for the first year calculus course, so it's a good idea to review this. A geometric sequence is when you have a list of numbers, and if you take a number in the series, in the sequence, and divide by the previous number, you always get the same answer. And so 16 divided by 8 is 2, 8 divided by 4 is 2, 4 divided by 2 is 2, and so on. And so we have a constant multiplier of 2, which we call R for these types of sequences. The first term of a geometric sequence is always called A. So in our example, A here is equal to 1. So when we add together all of the terms of a sequence, it now has the name of series instead of sequence. So series denotes that we are adding or summing all of the terms. So for geometric series, when we add all those terms together, the sum of n terms, that's what S sub n stands for, is what you would get if you could add together each term from A, the first term, all the way to n, the very last term. If we know the number of terms that we want to find the sum of when we have a geometric series, then we can use the formula I have shown here in the white box. Now, in this formula, we have a couple of terms that might look a little bit different, so let's talk about those first. The first is this symbol here, which is the Greek letter sigma, and it just tells you to find the sum. At the bottom, you see where it says k equals 0. K is representing the number of times that we're multiplying R as we go through our sequence. So in the first case, for our first value, our A value, then we would have an exponent of 0 on the R because we are multiplying the first term by 1 only. It's not being multiplied by that multiplier. And so at the top, you see n minus 1, and that represents the exponent. By the time we get to the end of our n terms, then the exponent of the multiplier will be 1 less than that because we started with term 1 having an exponent of 0, so term n would have an exponent of n minus 1. So we can use this formula to find the sum of any finite number, in other words, any definite number of terms in a geometric series. I've chosen the series that we talked about on the previous slide, and I have the first 5 terms of it written out here, and we could just add those up and get this sum because it's only 5 terms. So we know that the sum that we're looking for is 31, but let's use this example to see how this other formula will work in more complicated questions. We need values of A, R, and N to put into the formula. And so finding the sum of the first 5 terms of this series means that we're going to put in 1 for A, 2 for R, and 5 for N because there's 5 terms. And in the denominator we have 1 minus R, or 1 minus 2. So now we have 1 multiplied by 1 minus 2 to the exponent 5. 2 to the exponent 5 is 32, so that's 1 minus 32. And on the bottom we have 1 minus 2 is negative 1. So the sum of the first 5 terms of this series is going to be 1 times negative 31 over negative 1, or 1 times 31, which we already knew from previous work that is going to equal 31. Now, if we have a series that's infinite, that keeps going on forever and ever, and we're being asked to find the sum of it, then obviously that takes a little bit of thinking, because we can't find the sum of an infinite number of things. However, if this series converges, and by that what I mean is that as you keep adding more and more successive terms together, you're getting closer and closer to one specific value, then the r value must be between -1 and 1. If that condition is met, then we actually can find the sum of an infinite geometric series. The formula is going to change a little bit from what we were using before, because if we're going to put a fraction between 1 and 0 in for a value of r, which is an exponential, it has an exponent on it, then if you think about a fraction such as 1/2, we're going to multiply that 1/2 times 1/2 times 1/2 times 1/2 n times. And if we make that an infinite number of multiplications, then that is going to become really, really close to a value of 0. So that's going to make the top, or the numerator, just equal to 1 minus 0, and then we have the 1 minus r on the bottom. And so our formula in this case will simplify to a times 1 over 1 minus r whenever you're asked to find the sum of an infinite geometric series. Whenever you need math help for a math course or any other course at Trent that requires you to use some math, then please feel free to contact me at mathhelp@trentu.ca. You can book an in-person or an online math help appointment.